Let's get started today. Glad to see you're all pretty chipper and active. Sometimes on cloudy days, there's almost no noise. Today, it looks like you're pretty awake, which nice day for it. So today we are moving on to some new data structures. It's kind of you're being introduced to all the different data structures we're going to be considering for the rest of the semester in like this 2-week period. So we talked about lists and DQs for the last week. Now for the next week, we'll be talking about sets and maps. Once we're done doing that, you'll have been introduced to all the data structures we're going to be using except for stacks. And we'll get to that in a few lectures. But the rest of the semester after next Thursday will be spent, actually after next Tuesday, will be spent talking about how we implement all of these data structures. So we'll be talking about how you implement lists, stacks, DQs, queues, sets, and maps. And they all are what we call linked data structures. So they will use pointers. And that's why we covered pointers a couple weeks ago. And they'll also, with sets and maps, they will be using a second C++ technique, well actually a second general technique called recursion, which if at the beginning of the semester we said there's a couple techniques in C++ you still haven't been introduced to. One of them was pointers, the second one is recursion. So that's kind of a preview of what the rest of the semester looks like. So for the next week, that is today and Tuesday, we're looking at sets and maps, which are two more ways to efficiently implement find, insert, and delete, the three operations we've been looking at this semester. Before we do that, we want to take a quick look at something called Big O notation. And Big O notation allows us to talk about the running time of our different algorithms, because now we're starting to throw a lot of different data structures at you, and we want to be able to compare them as to when you should prefer one over the other. And the way that we do that is by looking at their time efficiency, their running time. So to compare them, we need a standardized way to talk about running time, and that standardized way is Big O notation. So in today's reading, you were asked to look at Big O notation, and we're going to simply today talk about how you're able to talk about Big O, compare running times. We're not actually going to look at how you compute running times. So we'll do that on the very final day of class, which I think is December 1st or December 2nd. So the very final day of class, we'll actually talk about how you can compute the running time of an algorithm. Until then, we'll just kind of give you those running times. So, but when we talk about running time, we're normally talking about the number of steps in an algorithm or the number of instructions. So up here, you see 5 plus 13n plus 7n squared. That would be, we'd be talking there about the number of instructions that a program requires to execute, or the number of steps it takes an algorithm. So that is basically the proxy we use for running time. We generally say that the running time is going to be proportional to the number of steps or the number of instructions that a program executes. Now, it's true that different instructions take different amounts of time to run. So a floating point arithmetic operation is slower than an integer arithmetic operation. But for the purposes of computing running time, we simply assume that all instructions take the same amount of time. We say they take one time unit. And that time unit is, we intentionally don't associate a specific measure to it like 1 millisecond or 1 nanosecond. And the reason is that CPUs have different speeds. And therefore, what is 1 nanosecond on today's ultra-fast, GPU might be 10 nanoseconds on a slower 2015 CPU. So we just say a time unit, and it's a time unit is essentially one instruction. Okay, so again, the important point here is that we're assuming that each instruction takes roughly the same amount of time, even if it differs by a constant. We don't really care about constants. So we count the number of instructions in a program, and let's say we come up with this number, and n is the size of the input. Okay? So an important thing here is n, which is the size of our input. And while orange is both our color and the color of the season, it's not a particularly easy color to read, so we will select black. So n is the, n is the size of the input. And it makes sense that as the input size gets bigger, you would think it would take longer for a program to run. So this is pretty intuitive, or should be. So when we're considering big O notation, we first have to compute the running time of our program. That's what we'll do the last day of class. So for the time being, I'll just give you the running time. Okay? So it's a function of n. Now, when we talk about big O, all we care about is the highest order term, or the biggest term. And we throw away everything else. So in this case, the biggest term is what? N squared. So we throw away the 5 and the 13n, and we get 7n squared. But you'll remember I said we don't care about constants. So we also throw away any constant in front of the n squared, and that produces our final order n squared. So we say the running time of this particular algorithm is proportional to order n squared. Notice I said proportional to, because it's going to be, there are two different algorithms could be both proportional to n squared. One might run faster because of constant factors, or maybe because its n factor is smaller. So it's proportional to it, but it's still going to vary somewhat because of constants and what these other ones are. But as n approaches infinity, okay, as n goes to infinity, so as n gets very large, the other terms disappear in terms of order of significance, and only that big n squared term is left. So that's the idea behind big O notation, is that as n gets large, the other terms essentially fade into irrelevance. So when we talk about running times, henceforth, we're going to be using big O notation. And I say big O because it is a capital O. And again, we only include the biggest term, and we drop the coefficient in front of the biggest term. So questions about that? Yes, John? It's a mathematician's thing. It comes out of math. So they introduced it, and I don't know why they used O. There's also, as you'll see when we consider it on the last day of class, there's theta, there's omega. So they've come up with a whole bunch of mathematical symbols to talk about it. So not sure who came up with the note with big O. Okay, other questions? So there are some things with big O that should be fairly intuitive. If you multiply big O by a constant, it's the same as that big O. If you add a constant, you also can ignore the constant because f of x is bigger than that constant. If you multiply by some g of x, you have to move the g of x into that big O, because if you have x times x squared, it's now x cubed. And if you add 2, this is the one time you'll see it as g of x plus f of x, because you might not be able to distinguish the two always. Okay? Now, more commonly, what you'd see is that you would have g of m plus f of n, and then you're not sure which is the biggest, and normally you would see that written as g of m plus f of n. So sometimes you have two inputs, and you don't know which is bigger. A good example is the PGM files you worked with. The rows, and you don't have to have a square matrix, okay, or a square picture. It could be rectangular. So you might have more rows than columns, or you might have more columns than rows. So you're really not sure what it is. So in fact, the time to look through all of the pixels in a PGM file is order rows times columns, because we don't know which is bigger. So we have to say both. Now if it was square, then we could simply say that it was order rows squared, because now we know it's a square matrix. But if we don't know that it's a square matrix, then we don't know which is bigger, and we have to include both terms. Okay, that's not as common. Most of the time, we have a single input variable. The input can be described with a single variable, but occasionally the input requires two variables. That's most common with things like matrices. Okay, so the most common things that you will see, there's one that is not shown here, and that is constant time. So we have log n log n squared, n cubed, 2 to the n. And you can see they have very different running times. If you get up here to 100,000, they ran it on some machine, we're not sure what, but you can see that for 100,000, log n is blazingly fast at 16 milliseconds, so you couldn't even blink your eye and it would be done. With n, it's a second, so you could certainly blink your eye, but it would still be fast. N log n is still pretty good. It's under 2 seconds. But once you get to n squared, you can go get lunch. There's a big difference between n log n and n squared. And so we are generally looking for algorithms that will run in n log n time or less. Okay? And you'll often hear n log n referred to as log linear, because there's a log factor and times a linear. But log grows so slowly that most n log n algorithms feel like a linear algorithm, even though they're not. Okay? But the log n grows slowly, and therefore it's the inverse of an exponential. An exponential blows up very, very rapidly. So if you look at what an exponential function looks like, it blows up super fast. You had 2 to the x. Well, the inverse of 2 to the x is log, so it goes the other way. Log 2 of x, which is the inverse function, grows very slowly and tends to flatline, or looks like it flatlines as n gets big. Okay, so n log n feels like it is linear, but n squared doesn't. Now we can't get away from n squared in some situations. With a matrix, you can't get away from having to look at the entire matrix. Or if you multiply two matrices together, you get close to n cubed, because it just turns out that matrix multiplication, multiplying two n squared matrices together, remember you did the dot product in the first exam, basically to compute each element of the new matrix. When you do matrix multiplication, you have to compute a dot product, and that dot product is order n. N times n squared is n cubed. And look at that. For 100,000 items, it's 31 years. So even with super fast computers, n cubed really is bad. But it gets even worse. There are some algorithms for which we know no better solution than an exponential one that takes 2 to the n time. And there you can see that even for n equals 50, it's 35 years. And for n equals 100, it's not even in the realm of discussion. It's so big. So a commonly used example of such an algorithm is the traveling salesman problem. So for exponential, you often hear the traveling salesman problem. So the traveling salesman problem says that a traveling salesman has to go to n different cities, let's say 50 different cities. The traveling salesman does not want to visit any city more than once, obviously, and wants to minimize the number of miles traveled. So it's very simple specification. Visit all n cities, visit each city once, minimize the number of miles traveled. It turns out there is no efficient algorithm for determining the best itinerary. That is the order in which the city should be evaluated. The best algorithms are effectively no better than simply trying every permutation of cities, or n factorial. Okay? Please don't go off and try to spend time coming up with a better algorithm. Very outstanding minds have spent years trying to solve it, and it's now conjectured that there in fact is no polynomial time solution. But the biggest outstanding problem in computer science is the so-called problem of does P equal or not equal NP? And we'll get into that question the last day of class, but essentially we know that the traveling salesman problem and other like problems fall into a class called non-deterministic polynomial, or NP. And they only have known exponential solutions. The big question is there a polynomial algorithm that solves any problem in that class? If there is, all other problems in the NP class will collapse to P. It is conjectured that P is not equal NP. There is no proof of that. Given how long mathematicians and computer scientists have tried to prove it one way or the other, it's now conjectured that there is no such proof. In math, you may have learned that there are some problems or conjectures for which a statement proposition is either true or false, but there is no proof. It's outside the system, the mathematical system. Given the set of axioms, it's impossible to prove it one way or the other. It's now conjectured that it is probable that P is not equal to NP. It's also conjectured that no one will ever find a proof for that. Okay? So don't spend your time worrying about it. I know I wasted a couple days in graduate school thinking I had the polynomial time solution. It was a wasted couple days. I didn't. Okay, so what do these things look like? So let's actually talk about the other one we love is 1, the function constant time, which we denote as 1, which is constant time. Because it doesn't matter how big n is, it's the same. It would basically be on the order of a nanosecond. And no matter how big n got, it would still be a nanosecond. So an example of a constant time operation is an array access or a vector access. Just a second. I think I just figured out why. I think Outlook is being pinged. So no matter how big a vector or an array gets, you can always access any element of a vector in constant time. If you have a very good hash function, then no matter how big your input is, and you actually have a good hash function and your hash table is the right size, no matter how many inputs you have, accessing an item in the hash table, finding an item in the hash table, or deleting an item in the hash table will take constant time. That's why we love hash tables. Log n. You have seen a log n algorithm in your time at UT. At the end of CS 102, you saw it. It was an algorithm over vectors. Does anyone remember what that algorithm might have been? Binary search, very good. So binary search, given a vector of n sorted elements, binary search can find an element in that vector in log n time. Okay, linear you're very familiar with. That is just linear search through a vector. Takes order n time because you look at every element in the vector. And log n time you haven't really seen, but if you were to do n searches using binary search, that would be n log n because each search takes log n time, hence doing n of them is n log n. It turns out that the most efficient sorting algorithms like quicksort and merge sort take n log n time. So the sort function that I showed you on Tuesday, it takes n log n time. Okay, n squared, it's the time to look through a square matrix, to examine every pixel in a square matrix, order n squared. We talked about n cubed and 2 to the n. Okay, so for those of you who prefer something more visual, here's the figure for that. You can see right now what's checked is 1 and log n, and there's only 10 elements, but they're just trying to show you the graphs. So constant time you see is a constant, 1. Okay, log n, very slowly growing. At 10, it's still less than 3 because log 2 of 10 is, well, it should have been actually over 3 because log 2 of 10 is about 3.3. So this should have been a little, but you get the picture that it grows fairly slowly. Now we add n. Okay, n takes linear time. As you would expect at 2, it takes 2 time units. At 4, it takes 4 time units. At 6, it takes 6 time units and so on. So you can see it's growing a lot faster than either of our previous ones. Now we do n log n, and you see that it's not really growing that much faster. It almost looks linear, right? There's a bit of a curve, but if you try to draw, and there's a slight curve here, but if you put a ruler to it, it would look pretty much like a straight line. Just a little worse. N squared, though, notice what happens. Here's the line, the green line for, here's the lighter olive line for n log n, n log n knocks it down. Here's the green line for n log n. When I go to n squared, notice how this green line gets knocked way down. And the reason is we had to really add a lot of computations. For n log n, we only had 100 computations. Whoops. I keep running. For n log n, we had 25 computations. For n squared, it's all the way up to 100 because 10 squared is 100. Okay, 8 squared is 64. So it's growing a lot faster. It's basically 5 times slower even at 10 for n squared. Now we go to 2 to the n, and even n squared is now way down because 2 to the n is over 1,000. And then here is actually the traveling salesman at n factorial, and at 10 it's already up to, what is it, 30 million? Maybe, no, 3 million. So the traveling salesman is just horrible. That's why they didn't even show n factorial. It was just so bad. Okay, so we generally try to avoid anything worse than n cubed. They didn't have n cubed here, but we try to avoid anything worse than n cubed. In fact, if at all possible, we avoid anything worse than log linear, n log n. So questions about big O. Okay, the last thing is when you see big O of 1, that is constant time. You don't write big O of c because, again, we don't care about constants. So if something is constant time, rewrite big O of 1. Okay? So with that in mind, we can actually characterize the running times of some of the data structures that we've already seen. Okay, so with a we have find. Our operations we care about are find, insert, and delete. And thus far, we have seen lists and hash tables as our primary ones. Okay? So in a hash table, we can also talk about best case or average case and worst case. Average and worst, average and worst, average and worst. So for hash tables, on average, if you have a good hash function and the right table size, the running time for find, insert, and delete any operation is order 1. What is the worst case when the hash function is horrible and it hashes everything to the same bucket? So all n elements go to the same bucket. N, because now it reduces to a linear search. So if your hash table is really bad or your hash table size is too small, it could get as bad as order n. That's why we kept the load factors below 1/2 when we were doing our open addressing schemes, because especially with linear probing, if the load factor got greater than 1/2, you started to move toward order n. But hash tables in general should take order 1 time as long as you're careful. Now with lists, even if you have a sorted list, you may potentially have to, with a find, go through the entire list. So with a list, the time to find something is order n, because you may have to look at the entire list. Now, once you have found where to insert or where to delete, you can insert or delete something in constant time in a list. Okay, so given the fact that you have found, so now I'm going to say that for lists, insert and delete are order 1. Now that comes with a huge caveat. Okay, these numbers right here assume you've already done a find, assumes you have already found, have already done a find to locate where to insert or to locate the item to delete. So in fact, the entire operation involves both a find and an insert, or a find and a delete. So the entire operation is order n for insert and delete. So the entire operation, okay, so the composite insert or delete is order n, because you have to always do a find first. That's where you get n plus 1. It's basically order n plus 1 equals order n, because the find takes n time, the insert or the delete takes constant time, because you're just rearranging pointers. Okay? With a vector, it takes order n time to do a find and a delete if it is unordered. It also takes order n time to do your inserts and delete, because you have to move all the items to the right. All the items to the right for an insert have to be pushed one element to the right. For a delete, the hole has to be filled. So that's why we prefer lists to vectors when we're doing inserts and deletes. Okay? So those are the big three we've seen so far. Now, if you insert at the back of a vector, that's different. If you insert at the back of a vector, it's order 1. So that's why we say if you only insert at the back, then you're good. So if we insert only at the back, so I have here back, now it's a lot better. Okay, find is still order n, but your inserts and deletes now become order 1 for a vector, because if you're only doing it at the back, you don't have to move anything. So that's why we say if you're only inserting or deleting at the back, use a vector. So you can see, using big O, we can start to compare things and determine which data structure might be better. Today we introduce a new one, and I'll just tell you, give you a sneak preview. Let's get rid of this at the bottom here so I can put in a little more into my table. We are going to be looking at sets and maps. And I can tell you that for a set or a map, either one, the average insert and delete times are all log n, both worst and average case. So we're going to be looking at another log n. And remember, in computer science, when we talk about log, what is the base? No, not 10, it's 2. Always 2 in computer science. So we don't ever put in the base, but in computer science, it's always log 2 that we're talking about. So both the average and worst case for sets and maps will be log n. So the first thing you should be asking yourself is, in comparison with a hash table, which seems to be better, a set or a map? What do you think is more common for a hash table, the average case or the worst case? The average case. We don't use look, unless you're a complete, I don't know how, I don't want to use derogatory term, unless you're really incompetent, if you implement a hash table properly, on average it's going to be order 1. Okay, that's why we talked you through things like load factors, hash functions, is so that you will choose a good hash function, so you will choose a good table size. You will generally get order 1 behavior. So if you get order 1 behavior, based on what I've told you, which of these two data structures is better? Always. Hash tables. Constant time is better than log n. So why am I going to torture you with sets and maps, given that, according to this, hash tables are always better? Well, 2 reasons. First of all, suppose this is a life or death situation where we can never afford an order n mishap. Maybe this is the space shuttle, and in an emergency, we can't have the computer using order n operations because the space shuttle might crash before it figures out what corrective action to take. And log n is good enough. Remember, log n is still much better than n. So it might be that in certain extreme situations where performance, worst case performance trumps best case performance, sets and maps are better because they guarantee a better worst case performance. Now that's pretty rare. Okay? The more common situation is this one. Let's say that I tell you that the items must be kept in sorted order. For some reason, here's an example. In the operating system, When you submit processes, your programs to run, your program is not the only process or program executing on the operating system. For one thing, the operating system is executing. The operating system has various tasks. It's performing file operations. It's looking at the input devices. It may be rendering things to the screen. So the operating system's doing various tasks. Your program is doing various tasks. You may have multiple programs running on your computer at the same time. Right now I have Camtasia running. I have Notebook running. I have Chrome running. I have a program called Emacs running. I have the terminal window running. So there's other programs running. Programs are given priorities. Some programs, like those in the operating system, have a higher priority than your tasks. So when it comes time for the CPU to schedule a task, it always wants to select the highest priority item. Well, to do that, the most efficient thing to do is to keep the programs in sorted order by their priority. Well, in that case, hash tables don't work because hash tables can't keep things in sorted order. The whole reason hash tables work is they randomize the key. So hash tables cannot keep your data in sorted order. So if I impose a requirement that the items be kept in sorted order, and there's good reasons to do so, as I just explained with an operating system, keeping track of which, it's basically a priority queue. It's keeping track of, for scheduling purposes, which programs to schedule next. It has to keep the programs in sorted order by priority. In that case, sets and maps with login are better because you can't use a hash table. Well, you could. The hash table would require now an order and search because the items are in random order. That's no good. So anytime you need to keep items in sorted order, you use a set or map. Another reason you might want to keep items in sorted order are for things called range queries. So if you have a range queries, you often do range queries. So they ask for things in a range. They're where you want, say, all things where x is between 10 and 30. If you keep things in sorted order, you simply search for the item that starts with 10, and now if they're in sorted order, they're contiguously next to each other, or in some ways, conceptually contiguous. You just run through until you get to 30. But again, in a hash table, it's no good because the items from 10 to 30 are scattered all over the hash table. So I used to be a runner. I used to be one of the best runners in Knoxville, in fact, and I used to like to keep tabs on who was just a little bit faster than me. And the Knoxville Running Club did keep track of race times. So I would be running around a 17 and a half minute 5K. I wanted to know who was running 16 and a half to 17 minute 5Ks. So I wanted to print out every individual between 16 and a half to 17. So I could try to stick with them during a race. Okay, that's a range query. That's no good with a hash table because a hash table would be randomly putting those race times everywhere. Okay? So sets and maps are good for range queries, and they are good when we have to keep stuff in sorted order. Range queries being one of those things where we have to keep things in sorted order. Okay? Questions? Okay. So, I will tell you that Dr. Planck's description of maps and the book's description of maps a little bit different. And I don't care which one you use. So first, well, I do care. You have to use a map to begin with. But let's go to containers and go to map. So, clear. So a map is going to allow us to do insert, delete, find. And I'm not going to tell you, well, actually, I will tell you briefly how it's implemented in a moment. First, we'll go through the API or the interface. So to do inserts, there's two ways to do it. The old way and the new way. I'll show you the new way first, which is the books way. Actually, first of all, I have to show you how to declare a map. So a map, actually, let's do a set first, because Dr. Planck does sets first. Start with a set. Okay, so a set allows us to insert a single key into the set. Okay, so let's go here for a moment. A set allows us to only store keys, like for example, names. So maybe Brad, Smiley, Nancy. Okay, only a key. Let's say early voting opened yesterday in Knoxville. And before you vote, what does the person at the polling station very interested in, if it's a fair democracy? Before you vote, suppose you're registered. First of all, we'll assume you're registered. Okay? But what's important? Pardon? Okay, you're right. That is very important what you're voting. But before they even let you vote, what do they want to check? Your ID. So let's say you're registered. Do they just let you vote as soon as they see your ID? Yeah, I want to make sure you haven't voted already. We don't want to allow people to double vote. If I voted yesterday, well, I might like to go back today and tomorrow the day after and keep voting, but that's probably not what you want. That dilutes your vote. Well, a set is good for keeping track of who's voted. All we really care about is the voter IDs. In this case, the set would be voter IDs, like maybe we'll say V03, V810, maybe V91. All we care about is the voter IDs. Okay? Now, more often, we also want a value. Like with hash tables, we'd insert both a key and a value. If we want to insert both a key and a value, we need a map. So, for example, if we cared about, well, when you go in and they looked up your voter ID, you probably care, they want to be able to say, hey, nice to see you, Brad. So this would be the key, this would be the value. Okay, or nice to see you, Nancy. Actually, it's the keys that are kept in order, not the values. So just to make that clear, well, it doesn't matter. It was V91. What's important here is not that Nancy is in order. It's that the keys are in order. So Nancy is next. And then it would be Smiley. I don't have enough room for Smiley. You get the picture. Poor Smiley. This morning, I pulled the wrong we have two metal bowls, it turns out. I didn't realize this. We have the shiny one and Smiley's dull one. I didn't realize this, so I pulled the shiny one out of the dishwasher and fed her with it. My wife was like, you just used the wrong bowl. So poor Smiley doesn't get the shiny bowl. She gets the dull bowl. And the bowl went straight back into the dishwasher. Okay, so I've learned. At any rate, Smiley is suffering a second insult here because I'm not adding her to the map. So if you want a set, it's one item. If you need a key value pair, you use a map. Okay? So a set, you include it using set. So it's in the STL. And when you declare something to be a set, you need to specify what type of value it's storing, just like you did with lists. So in this case, it's a set of strings, and we're looking at owning books, a set of books. Okay, and with sets, you use the insert command to insert an item. You use erase when you want to erase an item. Notice you don't need an iterator. With lists, when you did erase, you needed an iterator. Not so with a set, you just give it the key and it removes that particular key from the set. Okay? And there's a count function that we don't really care about too much, but that's simple. Well, it could if we wanted to know how many people voted. The count function would be very nice. It's the number of elements in the set. I'm looking for their find function. Okay. Second. Why can't I find... Oh, wait a minute. Just a second. Oh my gosh, that's terrible. Okay, just a sec. Okay, so if you want to find whether something is in a set, you can use the count function. Count will return the number of items it finds in a set. Guess what? A set cannot store duplicate keys, so the count function returns 0 or 1. So if it finds the key, it returns 1. If it does not find the key, it returns 0. I don't suggest you use count. Okay, we're going to look at the find function in a moment. Okay, so count returns 0 or 1 for a set. Yes, so we're going to talk about multisets, which store duplicate keys, and in that case, count would be valuable because it would return the number of times that key occurred in the set. So if we allowed multiple voting, so you vote multiple times, and every time you vote it, we recorded that back, we would use a multiset, and then the count could give us a good count on the number of times you voted. Okay? So let's just take a look at Dr. Planck's notes for a moment because I want to also show you the find command. Okay, so here is something where Dr. Planck is going to read, we have a program called Simple Set Find. We read a number of lines from a file, like let's say that we're reading names. John Bevy, Max Inadvertent, and what we want to do is after we've read all the names, we want to be able to search, enter names, and see if they're in the set. Okay, so maybe this is like our voting. So we include the set. We're going to be storing a set of names. So from our file, we read our names. Get line F into S. So S is the name of the voter. Names.insert inserts the voter into the set. Now, after we have all the names into the set, we go into this infinite loop where we ask the user to enter a name. Then, if they didn't enter a name, if they hit Control D to end terminate the input, we exit. Otherwise, we call the find function. So I prefer that you use find, and find returns an iterator. Okay, so find returns an iterator. Whoops. So find returns an iterator. Should it succeed, then find, so on success, it returns a iterator to the node that contains the key. So again, you see we're talking about nodes. And on failure, it returns .end. So essentially a iterator to the sentinel node. Okay? So just like lists, we have sentinel nodes in our sets. So what he's doing here is checking to see whether he succeeded or failed with names.find equal names.end. So if it's equal to names.end, it was failure, and he says S is not in the set. Otherwise, S is in the set. Okay? So I would prefer that you use find in this course. It returns an iterator to the item. Now, the other thing that is nice with sets is you can sort things very simply. So let's say I wanted to print all of the names in sorted order. Well, a very simple way to do that would be to read it into a vector and call it the sort function. That would actually be more efficient. But another way to do it is to read them all into a set and then iterate through the set. So just like with lists, we can declare an iterator, but this time it's iterating through a set of strings. So just like with lists, we have to declare the type of value, the data structure and the type of value we're iterating over. So the first one, the while loop, is simply reading through all the names in the file and inserting them into our set. And then we have this loop which runs through all of the keys in the set and prints them out. And since they're kept in sorted order, the names will be printed in sorted order. Okay, so it looks like we're running through a list, but in this case we're running through a set. We use the same dereferencing operator. Okay, and if we ran it on this simple set of inputs, Jack Journey, Mackenzie Olympia, James Splotch, and Dylan Acne, you see they come out sorted by first name. Now, in the book, you may have discovered another way to iterate. Did anyone see another way to iterate other than with this fairly lengthy notation? Well, we will show it to you. Range-based for loops. So let's show you a range-based for loop. Whoops.
But so far your grade scripts have been using SD11 or SD not 11.
Right. So I was going to warn you about that. Okay. So that was, I need to show it to you, and then I need to give you the caveats, including what the grade scripts are. But you need to see it. Okay. So instead of using this for loop, there is what is called a range-based for loop. So you give it the type of the data value. In this case, the type of the key is a string, and you declare a variable. I'm calling it key, and you give it the name of the set. And now I could simply say cout key. So what it does, this very simple thing also iterates through each element of the set, and it returns them in sorted order, and then I can print them out. So now I try to compile this. And as the gentleman said, I get a warning on the Mac. Actually, I get an error message too because I didn't use int. So I get this warning, range space for loop is a C++11 extension. So many compilers, even 7 years later, have not implemented the extension. Our grade scripts, when they compile your program, do not use the C11 extension, and therefore don't use this for loop in your labs, or the grade scripts won't work. But you should be aware that this exists, and you might be allowed to use it at the office. Okay? Watch what happens now. So this compiled on my Mac, right? Watch what happens. In fact, I think I can say map into roster.txt, and it kind of works. Not very well. But everything is in sorted order here. Okay, but the roster is not what I wanted. There's roster.text. Okay. Wait, what did I just do? Map. I want it set. There we go. So it puts it into sorted order. Okay, very nice. Now, remember I got that warning message. I'm going to copy this one now over to the Hydra machines and show you what happens when we compile it on the Hydra machines and why you should not be, therefore, using it on the Hydra machines. Okay. Range-based for loops are not allowed in C++ 98 mode. Whoops. So our compiler is using C+ 98 mode. Now I could force it to change that. std equals, I think it's C++ 11. Hope this works. Yep. So by giving it the flag -std equals C++ 11, I tell the compiler to enable C++ 11 extensions. The grade scripts don't do that. Okay? So be aware of these range-based for loops, but don't get in the habit of using them. Okay, it's too bad because I think they're a very nice improvement over iterators. Much cleaner, less prone to bugs, less prone to syntax errors, but it is what it is. So questions about that? Okay. Now, as John, I believe, was pointing out, we also sometimes want to be able to store duplicate keys. If we want to store duplicate keys, we must use a multiset. The reason is if we try to insert a duplicate key into a set, it will fail. You can't insert a duplicate key into a set. The insert method will fail. So if you want duplicate keys, you use a multiset, which means you declare it as a multiset and you include a multiset. So here, where's this program? There we go. Actually, with set, you get multi-set. So we declare it as multi-set. And now we can insert duplicates. We won't really use multi-sets that much. You should just be aware, if you want duplicate keys, use a multi-set. Now, in general, you won't use sets very often because we prefer to store key-value pairs. Okay, generally with a key, we want to store a value, and therefore we use maps. So with a map, you include a map, and you need to include both the key type and the value type. The key type goes first. Okay, so coming down here, the key type goes first. That's the key value, and that is the value type. So here, we're storing a map of strings. The value is int. And in this case, what Dr. Plank is doing, he is reading in football players from the NFL in 2009 whose last name started with A, and he is counting the number of players with the same last name. So every time he encounters a player with the same last name, he increments the count by 1. Okay, so here is his declaration for names. Again, int is the number of players with that last name. So int is the number of players with that name. Actually, it's that last name. So his input consists of first names and last names, very simple. So he runs a while loop that reads into first name and last name. The first thing he does is he tries to determine whether that last name is already in the map. So he says names.find ln. And that returns an iterator, just like it did with a set. And if it is found, it returns, in effect, an iterator that points to that item. Otherwise, it points to the Sentinel node. So if it points to the Sentinel node right here, it's not yet in. So in this case, not in the map. So he inserts it with a count of 1. And notice he used this make pair. And the reason is that the insert function only takes a single value, and that is a pair. That's very annoying, that you have to call this make pair function, and it creates a class called pair, an instance of a class, and that class has 2 members called first and second, which we'll see in a moment. Okay, if it succeeded, so the second case, the else, it was already in. Okay, so already in map. In that case, we increment the count by 1. And charmingly, pairs, as they're 2, a pair is essentially a class, so class pair. And charmingly, it's public. And its 2 members are type 1 first, Yuckadmundo, and type 2 second. Shouldn't have capitalized first, it's lowercase. Too bad it's not key and value, because that would be a lot more user-friendly, but they name the fields first and second. So the first is the key, and second refers to the value. So the reason we're incrementing second is because that is the count field, the value field. And notice we use an arrow because we get a pointer. Okay, use an arrow not a dot. Okay? So then we run through again. When we're done, we have a count of all of the players. So we run through them from beginning to end using our familiar way of iterating through a data structure and print out the name using first. And I know that's confusing. That's not the first name. First, again, is the, going back to that pair, first is the key value, second is the value. So second is count in this case. And if we run it, we get the output we want. So the file, there's the file, all last names with A. There are some duplicates, so if I look for Adams, you see 2 right there. Here's some more Adams, more Adams. And if we were to run our program and put the output into temp and look at temp, search for Adams, we find Adams, number of players 7. And it is actually not using the right map. Notice something here. What do you notice about the last names? Are they in sorted order? No, that's because before class I was experimenting with unordered maps. What do you think an unordered map is? It's a hash table. And what do you think, where do you think you find a hash table? In which part of the standard? No, well, it's in unordered map, C++11. It's not in the C98 standard. So if I changed it to map, like I should have, and I changed all of these unordered maps, let's see, all my unordered maps. And I recompile it and rerun it. Whoops. And I was using, of course, I was using my range-based loops for grins. So I will just quickly, actually what I'll do, yeah, I'll do that. Standard equals C++11. And I run it with the roster. And I do temp. Now it's sorted. There we go, all in sorted order. Okay, now the book. Let's go and see the book used in place. If you looked at the book, which you should have when you did the participation activities, you would know that instead of using insert, it used in place. And with in place, you can do the natural thing of just giving a key value pair, ln, comma 1. So that's what the book used in place rather than insert. Let's take a look. Works fine if I compile it using the C++11 standard. Goes down in flames if I don't use the C++11 standard. Okay, not only, look at this, it's even worse. So if I try to use the C++ compiler in C98 mode, I get a warning essentially for the for loops, but I actually, for the in place get has no member named in place. So if you try to use our Hydra G++ compiler, don't use in place, which means what? Oh, the grade scripts use the C98 standard. The grade scripts grade my program. What function should I not be using in my labs? In place. So we need to use insert. So in the labs, make sure that you use insert. Make sure that you use this long version of iteration. Yes, it's a pain in the neck, but your programs will work. Okay, on Tuesday, we will talk more about sets and maps and finish up this discussion, and I'll also show you a quick sneak preview of how they're implemented.